Hi guys, in this video what we're going to look at is what's called continuously compounding. We're just going to have a look at some numbers first and then work it out in the general case. So if you have a look here and we consider a nominal interest rate of 5% per annum, what we're saying is that R is equal to 0.05, but we're not saying whether that's compounded monthly, daily, etc. And we're going to let I be the equivalent annual rate of interest. So we're going to investigate the value of I by increasing M, i.e. the number of times that it's compounded. And we're going to have a look at this table here. So if we take 0.05 and we say, okay, we're going to compound that once a year, i.e. a yearly rate, what we end up with is I is equal to 0.05. Now that shouldn't be too surprising. So if we have a look then and we decide to take a monthly one, remember what we do is it's 1 over the interest rate divided by however compounds we want, which in this case is 12 to the power of whatever the compound is, which is 12 in this case. You can see here that this now becomes slightly bigger at 0.0511 because it's getting compounded 12 times, so it's going to be slightly bigger than the 0.05 that we have on the yearly rate. This is all done in one of my previous videos. If we do it each week, in this case what's going to happen is it's going to divide it by 52 and then it's going to be compounded 52 times, which again you can see is getting bigger than this one here. And then if we do it every single day, you can see here now we're dividing by 365 and then compounding it 365 times, and it's getting slightly bigger. And notice how this now is getting only slightly bigger. If we keep increasing our M's here, guys, so if we say we did it, I don't know, 1,000 M's, this is going to get slightly bigger and it's going to go towards a limit. And you can see it tells us that it's going to tend to a limit. It's going to be 0.05127109664, correct to 10 decimal places. Okay, so this is the rate of interest if a nominal annual rate of 5% is compounded continuously. And what we mean by compounded continuously is just like every second, every millisecond, that we are adding on more and more M. So M is going to get bigger. M is basically heading towards infinity. Okay, so as M heads towards infinity, what's going to happen is this is going to go to a limit of 0.05127, etc. Okay, so we've already sort of had the idea of what it's going to be like with a number. So we're going to have a look at when it's just the bog standard idea. So I've already said here that what we're trying to do is we're trying to take M to the limit of infinity, and we're going to do that for this particular expression. So I is equal to the limit as M heads off to infinity of 1 plus R to the M to the power of M minus 1. And we had a chat there. We said R is the rate, M is the number of compounds it's going to have. So if we go back to that table for the monthly, R was 0.05 and this was 12 to the power of 12 minus 1. Okay, so what all we're going to do here is we're going to take this minus 1 across, so we get I plus 1 is equal to the limit here. So then we can now have a look at this limit, and we're going to look at that in the table in a second. Oh, by the way, this is called the force of interest, just if you're interested. Okay, so if we do this, and we start sticking some numbers through, so if we put 100 through this formula here, we get 2.70. If we put 1,000, you see 2.71, 10,000, 2.71814, and so on and so forth. And hopefully, guys, you'll notice that this is going to one of those really special numbers in mathematics. It's heading towards E. Now, good news. Formal proof of this is beyond the scope of our course, and it's something that you'll do at university if you do anything mathematical. But we don't need to do it, which is brilliant news. So let's have a look how this limit works. So we need to find this limit of M heading off to infinity of 1 plus R over M to the M. So we're going to arbitrarily say that X is equal to M over R. So we're going to introduce a new variable X, and we're going to say X is equal to M over R. Then this means that 1 over X is equal to R over M. Now, if you're not sure why that is, I'll just quickly show you. So what we have here is we have X is equal to M over R, and that's the same as X over 1. And if we start to cross multiply a few things, then what you'll find is that XR is equal to M, so that implies that XR is equal to M, which now means that 1 over X, we're trying to get this over to here, so what we're going to do is divide by M, so we get XR over M is equal to 1, which implies that we now have 1 over X is equal to R over M. Okay, so 1 over X is equal to R over M, which means that we can now put in for R over M in this formula, we can change that for 1 over x. Okay, that's going to be useful in a bit. We also know that m is equal to xr. I've did that here, you can see here. And as m heads towards infinity, well, that means x has to head towards infinity as well. Because as m gets bigger, that means x will get bigger. So what we're doing here now is we're changing this original, and we're saying the limit of m heading off to infinity of 1 plus r to the m over m, we can rewrite as the limit of x heading off to infinity, because of this here, 1 plus, and we change the r over m to 1 over x. And you can see here, because we have an m to the power of m, it's the power of xr. So that's the first line. The second line, all we've done now is we've taken the r outside because we're allowed to do that during our index laws. So now what we have is exactly the same as what's on here, apart from we've brought the r out. You can see here, it's exactly the same as what we've done. And from here, what you can see, essentially, is that all of this limit here, we've already proven on the previous slide, or we showed on the previous slide, that that's going to head to e. So this here is going to head to e, and then that's all, so this everything in this bracket here is going to head to e, which means we now have e to the power of r. That means that what we have here is 1 plus I is equal to e to the r, and I, therefore, is equal to e to the r minus 1. If we rearrange it, we can get the other way around, and we can get it in terms of log form here. And as you can see, it says, when interest is being compounded continuously, the nominal and annual rate of interest r is called the force of interest. If I is the equivalent annual interest rate, then I is equal to e to the r minus 1, and r is equal to log e1 plus r. And I'll show you how to do these, or how to use these two equations in the example on the next slide. Just out of interest here as well, if we have a look now of the formula of f is equal to your p, and remember it's 1 plus I to the power of t. As this is continuously compounded, this 1 plus I will change to e to the power of r. Yeah, so here look, 1 plus I becomes e to the power of r from here. So we now have f is equal to p, that bracket goes to e to the power of r, and then we have to the power of t, so f is equal to the principal to the power of e to the power of rt there. So PERT, so f is equal to PERT. Guys, you don't need to know on your course, it's never come up in the exam where you're having to prove any of what I've just shown you, but you do need to know, first of all, this, just remember if it's continuously compounded, then it's PERT. F is equal to PERT, P-E to the RT, and we do need to know how to use these, and I will show you how to do this on the next slide. So here we are, the interest rate for a large financial loan is quoted as 3.5% per annum, compounded continuously. Find the equivalent annual rate of compound interest as a percentage, correct to 5 decimal places. So remember the compounding continuously and force of interest, I've just parachuted that in from the previous slide. We can see that the I is equal to e to the r minus 1, or r is equal to log e1 plus I. And we are told the interest rate for a large financial loan is quoted at 3.5% per annum. So that means that r is equal to 0.035. Okay, we're finding the equivalent annual rate. So we're trying to find I. So we're trying to find I. So we're going to use this formula here. I is equal to e to the r minus 1. I is equal to e to the power of 0.035 minus 1. Whack that in your calculator, boys. If you do that, you end up with 0.0356197. Would you expect it to be bigger? Of course you would, because the annual rate of everything being continuously compounded, so you'd expect it to be bigger than your R value here. And that's it, boys. Hopefully this all makes a bit of sense. As I said, you do not need to know the proofs for this. You just need to be able and aware of what F is equal to PERT. Okay, so you need to be able to use that. And you also need to know these two formulas here. Okay.